Hello? This is going to be a short day. By design, we're going to wrap up 9.10, but we're not going to start 9.7. The lesson just before this one, the previous lesson, was some heavy stuff. And I want to give you guys time to let that sink in. There's no reason to rush the 9.7. So we're just wrapping up 9.10. That is the plan. We're going to prove the two theorems that we discussed yesterday. The proofs are both shorter than one might expect, in fact. It's kind of nice. We're going to talk about manipulation of Taylor series a little bit, and discussing the list of parent functions, so to speak. We'll get there to make a little more sense. So just wrapping up a few things for Taylor series. This will leave us with only one section of regular material left, which is 9.7. Though that's a little long. And then we'll see what else we're going to do. See what you guys think. See what topics we can explore a little bit. First, proving the uniqueness of Taylor series. The uniqueness of Taylor series. Technically, I suppose we should call this the uniqueness of convergent power series. But we know that that is the Taylor series. That's the point, right? So in practice, what you think of here is that Taylor series are unique. A reminder of the statement, we're saying that if I have a power series centered at C, which is known to converge to a function f of x, this implies that I know precisely what the coefficients must be. They must be, respectively, the nth derivative at c divided by n factorial. Those are the only options for the coefficients in order to converge to f of x. For our proof, and this is enough space, not a big one. By 9.8 and 9.9, it's actually only one of the two, but I can't remember which of the two this was in, sorry. We know that a convergent series implies that the derivative also converges. So given that we're assuming this series converges, we are allowed to take its derivative, and that derivative will also converge. With that in mind, let's write out the series and do a derivative. So at n equals 0, we'd get a sub 0 x minus c, to the 0 goes away. At n equals 1, we get a1 x minus c to the 1. At n equals 2, we get a sub 2 x minus c squared, etc. So when I take a derivative of both sides, that maintaining equality, technically because of properties of limits and stuff, we get f prime is, well, the a0 goes away. Here I get an a1. And then here I'd get plus an a2 times 2 x minus c to the 1. And the next term, which I hadn't written, would give us an a3 times 3 x minus c squared, and so on. Let's take another derivative. Let's make sure we see this pattern. We see what's happening here. The a1 goes away. I'd get a 2a2. We'd get a sub 3 times 2, and the power reduces. So an a3 times 3 times 2, and the power is a 1 now. The original a4 term, I would have differentiated and brought down the 4 power. Differentiated again now and brought down the 3 power. So we get an a4 times the 4 and the 3, and we'd be left with 2 pieces still. And the sequence continues. The series, continues. So I think we see a pattern here, right? If we go to f, the 0th derivative, and we plug in x equals c, that's what it says to do, plug in x equals c, goes away, goes away, goes away. Everything's gone except the a0. So at n equals 0, I get a0. At n equals 1 in my first derivative, plugging in c makes this term go away. Plugging in c for x makes that term go away. All the others too, I'm left with just a1. Or better, perhaps we could say a1 times 1. Or better than that, we could say a1 times 1 factorial. For n equals 2, when I plug in x equals c, this term goes away, that term goes away, all the higher terms go away. I have only 2 factorial times a2. And you can imagine what would happen next, right? The a2 would go away. We'd get a3 times 2, which is to say a3 times 3 factorial, but all of the higher terms would still have an x minus c factor, so when x equals c, they disappear. I conclude from this pattern that the nth derivative evaluated at c is a sub n times n factorial. And accordingly, a sub n is equal to the nth derivative at c divided by n factorial, completing the proof. That's it, whole thing. Wrote out some terms, literally wrote down derivatives, saw the pattern. That's it. It's a big deal theorem, but the proof is actually quite nice. So there's theorem number 1 and its proof, right? We'd introduced the theorem but not proven it last time. Here's the same thing, theorem number 2 that we introduced last time, and its proof. So this is Taylor's theorem. Oh man, I don't know why the focus is so weird. Come on, you can focus, you can do it. Okay. Which said that if I have a convergent power series which converges to some function f of x, the Taylor series of f of x, this will be true. I will converge to f if and only if the limit as n approaches infinity of the remainder term is 0. If we write f of x as a Taylor polynomial, a finite polynomial, plus a remainder term, the infinite series will converge to f if and only if the remainder term approaches 0. Makes sense. Seems okay. Proof. The Taylor polynomials each exist. P sub n of x exists. You literally just write it down. It's finite. There's no problem, right? You can't possibly have a convergence issue. It's finite. That said, this is provided f is, it's called C infinity. F is infinitely differentiable, right? Technically, I only need derivatives up to n, but I'm saying this exists for all n. So as long as I can do derivatives, I have my Taylor polynomials, my finite polynomials. Well, technically this is a step of algebra later, but we know that the nth Taylor polynomial is f of x minus the remainder. The definition step is that f equals the polynomial plus the remainder, right? And then I just subtract 1 over, no problem. And then the key is to note the following. The nth Taylor polynomial is the nth partial sum of the Taylor series. If I take the entire Taylor series and I just cut it off at n, that is the polynomial. That's a finite Taylor polynomial. The derivatives agree as we need. Everything is great. So let's take a limit of both sides. We have a limit as n goes to infinity of the nth Taylor polynomial is equal to a limit of f of x minus r sub n of x, again, as n goes to infinity. Well, oh, I still want green. The limit of partial sums is by definition the infinite series. So, if I assume the left-hand side, that my infinite series converges to f, then this bit exists, right? So for the left-hand direction, we're good right there. The limit of f of x definitely exists. There's no n in it. There's nothing to do, right? There's no n in the function itself. So that part definitely exists. And if I assume that the limit of my remainder is 0, then in that direction, in the assume the remainder, show that the series converges, then I would know the limit of my remainder exists. So if I'm trying to do the left to right portion of the proof, I know that these two pieces exist, and by known limit properties, if those two exist, the third must exist, right? I can split this limit up, and that's okay. If I'm going from right to left, if I'm assuming that the limit of the remainder is 0, then these two pieces exist independently, therefore I'm allowed to split up my limit. So either way, we can use a known limit property to rewrite this same expression as the limit as n approaches infinity of the nth partial sum is equal to f of x by itself minus the limit as n approaches infinity of r sub n of x. Two of the three are guaranteed to exist in either case. It's a different set of two, but that's all right. And I'd like to note that the limit of the partial sums, by definition, I'll explain the scare quotes in a sec, but by definition is the infinite series. I can't technically write that yet, hence the scare quotes, because one of the directions of this proof is proving that this thing converges, right? So if I'm doing the right to left proof where these are fine, but that I don't know yet, I can't write it. It might not converge, right? But notationally, this is what we mean, right? So in the left to right version, we're saying this converges, that exists, we're fine. And furthermore, it's equal to f of x. So if this is f of x and it's equal to f of x minus something, then the something is 0. End of left to right. No problem. Again, right? Our proof that we're trying to do, our statement we're trying to make is here. So left to right is this part exists and equals f, therefore, okay, we're done. Right to left, meanwhile, this limit is 0. Therefore, yeah, this thing has to exist. It's equal to something that exists. And that thing is f, which it had to be. Awesome. So we get that these two parts are equal if and only if this part goes to 0, right? If the limit of the remainder goes to 0, then yes, my series converges and it's equal to f. Alternatively, if my series converges and it's equal to f, this term over here, the limit of the remainder term, has to be 0. And that concludes this proof. Right? Not so bad either. A nice little combination. Works pretty well. And that's it for proofs. That's most of today's material. Okay? Little bit more. We talked about manipulations of power series already. So what if you wanted to do a Taylor series of e to the x cosine x? First, think naively. You certainly could apply the formula directly. Take derivatives of e to the x cosine x, plug in the center, whatever you choose, probably 0, right? That would be the easiest, but something else if you had to. And you could look for a pattern in those evaluated derivatives and try to write down a formula. In practice, that's going to be basically impossible. You could write down as many individual terms as you want. You can just take derivatives and do that. But there won't necessarily be a nice pattern. You might just kind of be stuck with writing the terms you evaluated and not being able to express a generic a sub n formula. What we could do instead, however, is use what we already know about the pieces. We derived last class a Taylor series for e to the x, specifically a Maclaurin series, right? We centered at 0. And likewise, a Taylor series, again, a Maclaurin series, we centered at 0 for cosine of x. For e to the x, it's 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. And that's not something you should have memorized just yet. It is something you're going to want to memorize eventually. That is part of your math toolkit that you should know at some point, now that you are at this level. Cosine of x, likewise, not something you need to memorize just yet, but something that you will want to have in your arsenal moving forward, right? Something that you will eventually want to know. 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial, etc. It helps me remember knowing that cosine is even, so I know I'm only dealing with the even terms. And we could do formal multiplication, same as we did with power series in general, because Taylor series is just a specific type of power series. What we could do for power series, we can do for Taylor series. So we have that e to the x cosine x is equal to, I'm just going to collect terms, so my x to the 0 terms. The only way I get that is when I do the 1 times the 1. No problem. I'll collect my powers of 1. So the x times the 1 gives me a power of 1, and there's no other way to get a power of 1. That's it. I'll collect my x squared terms. I get one of them from x squared over 2 factorial times 1. I can't make an x squared term with the x, but I do get another from the 1 times the negative x squared over 2 factorial. And we would continue. But of note, this is not a closed form. You're not going to be able to write a nice expression in terms of n that gives you the coefficients of each of these powers. So far we have 1, 1, 0. And x cubed is not 0. We don't get a closed form. And that's okay. Why would we ever want to do this? Well, for example, what if we were trying to integrate from 0 to 1 of e to the x cosine x? You know that you can use integration by parts. You'd use it twice, it'd be a swingy, and that's fine. That would work. But if this came up in an application, or if this were being computed by a calculator, and you only needed a value within a certain tolerance, right? Within a certain degree of error, it'd probably be a lot easier to work with polynomials than to have to do a bunch of analytic, abstract manipulation. Well, we know that this is precisely equal to plugging in the Taylor series. And we got a 1 and an x and no x squared, so we should probably write the x cubed term. I tend to suggest writing at least 3 terms for any series. So for the x cubed term, let's take a look. I'd get the x cubed over 3 factorial times 1, and I'd get x times x squared over 2 factorial, negative, right? So we'd get a 1/6 minus a 1/2. And that series would continue. 1/6 minus a half is negative 1/3. So we could approximate this integral by using only the 1, the x, and the negative x cubed over 3. That wouldn't be that far off. We don't know exactly how far off because we might not even be alternating, right? We don't have a good error term for this, unfortunately. But it would be a pretty decent approximation already. It would work fairly well. So why would you want to construct Taylor series for things without closed forms? Here's an example, right? It would give you a way of approximating messy functions. Second to last, nope, I lied. Third to last thing of the day. So that was example 1, manipulating Taylor series using formal multiplication. Well, you can probably predict what's coming next. How about we manipulate using formal division? We know a Taylor series for sine. We know a Taylor series for cosine. Sine is 1. No, I'm so sorry. I'm dividing, right? The cosine part. 1 for cosine plus. Let's keep track of all of the terms. It'll help in our division. And we're dividing into the sine term, which is 0 plus an x plus a 0x squared minus an x cubed over 3 factorial and so on. So for formal division, unlike what you usually do with division, right, we're going to match up this lowest power term with the lowest power. Oh, it's x, not 0. Okay, with the lowest power term. So 1 to get x, we have to multiply by x. And that would give me x and no x squareds and negative x cubed over 2 factorial and no x to the fourths, etc. We subtract, I get 0, I get 0, I get negative a sixth plus a half is a positive 1/3 x cubed, and 0x to the 4s, and I'd get some x to the 5s. To make 1 cancel the 1/3 x cubed, I would have to have a 1/3 x cubed, which would give me a 1/3 x cubed, as it should. It would give me no x to the 4s. It would give me a negative 1/6 x to the 5, and we would continue, right? We'd build up the series. If you recall, we found a power series for tangent back in 9.8 and 9.9. And it was x and x cubed over 3. Notice it's not factorial, just a 3. And then it was x to the 5 over 5, which, yeah, that's working out okay. Notice that we're only getting odd terms. That's kind of cool, because tangent is odd. Working out nicely. So you can use formal division to figure out a Taylor expansion. Again, this is based on the fact that Taylor series are unique for a given function at a given center. So any way of getting the power series, you're all set. Things are done. No problem. Last example. We did formal multiplication. We did formal division. Let's talk about substitution. You could find the Taylor series for sine of x squared by doing derivatives directly. You can. You cannot, however, integrate this directly. We do not know any function whose derivative is sine of x squared. It cannot be done. However, we could express this as a Taylor expansion. Imagine we're just using sine of y, so that's y minus y cubed over 3 factorial plus y to the 5 over 5 factorial. Again, not something you need to have memorized yet, but something you will memorize eventually as part of your advancement as a mathematician, right? Something that you will know, just like you know that 9 cubed, bad example, I don't know 9 cubed, is it 729? Yeah, I guess. Whatever. Yeah, it is. I do know 9 cubed. Better example, right? Like 9 squared is 81, right? Taylor series of sine, cosine, and e are things that you're just gonna know. Is it really 729 and I just knew that? Yeah, all right. I think I'm right. Okay. Which is to say, let's write this out. Now that I'm going to do the substitution, I'd get an x squared, I'd get an x to the 6 over 3 factorial, I'd get an x to the 10 over 5 factorial, etc. Which we can just straight up integrate. X cubed over 3 minus x to the 7 over 7 times 3 factorial plus x to the 11 over 11 times 5 factorial, and so on. And I chose to evaluate from 0 to 1. You could try to write this explicitly, and in this case, it's actually possible. Instead of evens and odds, it involves using powers of 4, right? Using mod 4 effectively in a way. Mixing it with evens and odds. It's possible. 3, 7, 11 is skipping by 4s, right? But for this particular problem, we're just going to plug in our bounds anyway. We get 1/3 minus 1 over 7 times 3 factorial plus 1 over 11 times 5 factorial, and so on. We know that if we plug in 0, we get 0. And hey, look, it's alternating. So we can approximate this value to any chosen degree of error, any chosen error bound, I should say, because we know the error bound is just the next term. And we have this nice pattern of terms. Great. We can find the value of the integral of sine of x squared from 0 to 1 to any chosen degree of accuracy by using Taylor series, by turning it into a polynomial. And it's just plain nicer that way, right? It works beautifully. Last thing of the day. So this is that parent function sort of idea, right? The equivalent for Taylor series. Series that you're going to want to outright know. You're going to want these memorized. These are going to be facts that you just have at your disposal for future math and science endeavors. You're going to want to know e to the x straight up, and cosine of x, and sine of x, and 1 over 1 plus x. That last one, notice, you do by geometric series. Don't do derivatives at all, right? Just that's a geometric expansion with common ratio negative x. No problem. You should be familiar with, but not necessarily just memorize. I don't recommend intentionally memorizing these. 1 over x at x equals 1. I'm sorry, c equals 1. Rather than at 0. Can't do that one at x equals 0 anyway. Natural log of x, also at c equals 1. We can't center at 0. It doesn't exist there. Arctan of x. Other trig, for example, arcsine of x could be useful to know. Maybe arccosine. And 1 plus x to the k. You should, well, not pause yet. Let me explain what you're going to think about while paused. This last one should seem like a bizarre bit on the list, right? If k is just 2, for example, you wouldn't use a power series. You wouldn't make a Taylor series. You would just square it. 1 plus 2x plus x squared. That is a Taylor series, though, right? It's just that it's 0x cubed, 0x to the 4, 0x to the 5 forever. If k were 3, it'd be a Taylor series. 1 plus 3x squared plus x cubed. It's a finite Taylor series, though. It seems pointless. So you should pause for a second and think, why is this on the list? Right? This seems pointless. You just multiply. You wouldn't bother with Taylor. Pause and think for a sec, but not too long. The reason this last one is interesting and important is because I never said that k has to be an integer. I kind of led you into that, right? Because I wanted you to try to figure out, oh wait, what if it isn't? But that's when this is interesting. Things like the square root of 1 plus x, you can make a Taylor series. Things like 1 over 1 plus x, when k is -1, you can make a Taylor series. And that Taylor series, the expression we'll get depends on k. Depends on k. These are in your book. However, I strongly recommend, in fact, I require as part of this course, for at least one of these, you need to derive the series yourself. Just one is okay, or more is okay, up to you. When doing the homework for 9.10, if you choose a problem that uses one of these and you derive it on your own as part of the problem, instead of looking it up and using the known series, that counts. But if in your homework you don't use any of these, or if you do use these but you look it up instead of deriving it, I expect you to separately add a problem, which is derive one of these directly. Okay, so I am requiring that you derive one of these yourself. Up to you which. More is up to you. But when I say derive, I mean not only the series itself, and their intervals of convergence. It's actually really important for these. And I would encourage you to find the intervals of convergence for these four yourself. And I'm requiring that the one you derive down here, you also evaluate the interval of convergence. Remember, Taylor series are power series. It's just a special kind of power series. And you know how to get the interval of convergence of a power series. If you used a geometric series to get your power series, use what you know about convergent geometric series. You're done. If not, if you use some other method, manipulation or doing it directly with derivatives in the case of a Taylor series, ratio test. And then make sure you think about your endpoints. That's it for the day. So, recap. We've wrapped up 9.10. Today we talked about proofs of two theorems, we manipulated Taylor series, and we talked about what you should know from this, right? What should be part of your toolkit. Uniqueness of Taylor series with its proof. We just literally did derivatives and plugged in C's. Proof of Taylor's theorem. We used some older material, some manipulations of limits, some definitions of infinite series, and made our conclusion both ways at once, in both directions. That was an if and only if statement. We talked about using formal multiplication to derive Taylor series instead of having to use derivatives every time, and why we might want to. We talked about using formal multiplication to derive Taylor series instead of having to do derivatives every time. We talked about being allowed to use substitution in Taylor series and why you might want to. This is a particularly nice example. We cannot solve this any other way. I mean, I guess you could use Riemann sums, right? You could approximate with Riemann sums. So we could do it that way also, but this was way, way better, right? This wasn't bad at all. And we talked about what you should end up having in your toolkit. You should end up memorizing, not necessarily sit down and do it, but as you work, you will end up memorizing Taylor series for e to the x cosine x sine x and 1 over 1 plus x. I suppose 1 over 1 minus x too, but again, that's just because it's geometric. That's all. And you should be familiar with, you should be able to recognize 1 over x, ln of x, arctan of x, probably arcsine, but maybe not. That one's a little sketchier. And binomials, except k doesn't have to be a positive integer. It doesn't have to be a natural number, and that's the cool bit there. These are ones that if you see things, you should be able to say, wait a minute, I'm pretty sure that's one of our basic functions. I'm pretty sure that series is something I know. These, you should just know. You should be able to do them yourself without having to look them up. I'd like to emphasize, in particular, this substitution idea is a big deal. Just heads up on that, okay? looking at this, it's really hard to look at that and say, oh, wait a minute, that's sine of x squared. That's really hard. The only way I'd think of to even, I'm sorry, the integral, looking at this one and saying that's sine of x squared, I would figure, well, all right, hold on. It's only every other, it's skipping numbers. The denominators are the odds, and okay, it's alternating. The numerator, you gotta look for clues. But it's hard to do. It's hard to backtrack for Taylor series. Okay, be aware. Should have mentioned that at first, sorry. That's it for today. That's it for the week. Just about a half hour, yep, perfect. As always, contact me if you need anything. All right, you don't have to do this on your own. Let me know if you have questions. I'm happy to work with you. And have a good day and week.